Hey everybody, new plan. I'm going to be making a separate assignment, a separate Google Forms document for each video, and the name on the Google Form assignment is going to match the video. So watch for that. I'll also put the link in the comments for each video. Have fun. Okay, so we were just talking about electron motion and how electrons move, but not really as much as you would expect um, in a wire. Instead of moving, actually, when we talk about electrons moving in wires, we use the word drift, which suggests that they don't really move all that fast at all. So let's look at that. In this section about electric current, so the word current, think about like the current in a river, right? The electric current, the reason we have that word current is because we think about the electrons moving as opposed to static electricity, where we think about the electrons sitting still. But it turns out that these words don't quite work out the way they should. So let's read here. It says, explain. Electrons in a typical household circuit drift only about 1 centimeter an hour. Yet, when you flip a light switch to close a circuit, a lamp in the circuit will begin shining almost immediately, no matter where it is in the circuit. Explain why the lamp turns on so quickly if the electrons drift so slowly. So as usual in this book, they ask us a question, and now they're going to give us the answer and ask us to think about it, and then we'll write up here what we think the answer is. An electric circuit is a closed loop through which charge can move continuously. When a voltage is applied to a wire, an electric field is generated throughout the wire, and a force acts on all of the electrons in the wire. While a single electron may move erratically, it is the net movement of charge in the wire that affects how the circuit behaves. So up here we have our one electron looking at the black line, our one electron bouncing all around, but drifting to the right here. If you measure the rate and direction in which charged particles move through a cross-section of the wire in a circuit, you will notice a net flow of charge in one direction due to the electric field. The rate at which the charge moves through this cross-section is measured in amperes, capital A is the abbreviation, or amps, where 1 ampere is equal to 1 coulomb per second. And remember, a coulomb is a measure of a number of electrons. Now in figure 4 here, what they're trying to show us is a cross-section of the wire. That's what that kind of gray area there is a cross-section of the wire. And we have 2 electrons moving through that cross-section in that direction. And this one is moving, whoops, this one is moving kind of in that direction. So looks to me, I'm just kind of trying to get a sense of the average movement of the electrons. Maybe they're moving to the right. Anyway, the point is we're interested in the movement of a charge through a cross-section of a wire. 1 coulomb per second is 1 amp. So here we have a model showing the directions of electron drift and electric current in a circuit in which the positive and negative terminals of a battery are connected by a wire. So here's positive, and here is negative, and the current is moving in this direction, around like this. So take a look at the direction of electron drift. The yellow line shows the direction of electron drift. And we've got to look around the yellow line and find where the arrowhead is. And here is the arrowhead. So the arrowhead down here is pointing to the right, which means that on the other end of the battery, it must also be pointing to the right. And it must be going around the circuit in a counterclockwise direction. Now let's compare that. Let's compare that to the direction of the current. The direction of the current, shown by this arrow right here, is moving to the left as it leaves the positive end of the battery, and around to the left again as it comes to the negative end of the battery. So let's look at the next section where it says analyze. According to figure 5, what is the relationship between the direction of electron drift and the direction of electric current? A, they're the same. B, they're opposite. C, they're not related. You can answer this question in the Google form. There's a link to it on Google Classroom. And so they're going to explain what they mean by this question. A battery in a circuit provides a voltage that generates an electric current in the circuit. When current was originally described by Benjamin Franklin, by the way, the American Benjamin Franklin, he's on the $100 bill. When current was originally described, it was thought that the charge carriers moving in a circuit were positively charged. It was later discovered that the charge carriers were actually negatively charged electrons. However, the convention for the direction of current was maintained despite the discrepancy. Discrepancy means disagreement. It means the two things are different. And convention means this is just the way we've decided to talk about things. So due to this convention, electrons actually drift in the opposite direction of the current. So think about what that means for answering this analyze question up here. The electrons carry the charge, and so the electrons are negatively charged. They're going to be leaving the negative end of the battery, going around the circuit, and being attracted, if you want to think about it that way, negatively charged electrons being attracted to the positive end of the battery. So compare that to what's going on with the current in that diagram. Now, this actually might be kind of a fun thing to do here, the language arts connection. You can work on that on your own if you want. Direct current. A battery has a negative and a positive terminal that provide a voltage in a circuit. Actually, what we would say is that there is a voltage potential between the positive and the negative part of the circuit, and the conventional current goes in this direction, goes from left to right. We've just talked about what the electrons actually do. So there's an electrical potential between the negative and positive terminal of a battery. Electrons continually drift toward the positive terminal in a circuit with a battery. When electric current flows in one direction only, it is called direct current, right? It goes from the negative terminal toward the positive terminal directly. Flashlights and other portable electronics with batteries, this should be use direct current. We should say that they use direct current. Just going to do a little editing here. They use direct current. Photovoltaic cells, which generate electrical energy from sunlight, also produce direct current. Infer. describe what would happen to the current in the circuit shown in figure 6 if the battery direction were reversed. So right now we are looking at electrons leaving the positive end of the battery, and I'm sorry, that's not what we're looking at. What we're looking at is we are looking at the electrical current moving from the positive end of the battery. This is the conventional current moving from the positive end of the battery around toward the negative end of the battery. And we know that the electrons are doing something different. In fact, you can see if you look closely at the diagram that the electrons are moving that way. The blue arrows show which way the current is moving, and that red arrow I just drew show which way the electrons are moving. So the question is, what would happen to the current if the battery direction were reversed? So if we just swapped the ends of the battery like this. So I'll let you think about that and write about that in the Google form in Google Classroom.